In this video, we're going to be taking a look at something called the chain rule. The chain rule is essentially what allows us to take the derivative of a composition function. So if we're given a function y equals f of u, and it's a differentiable function in terms of u, and then u is a function in terms of x that's differentiable, then the function y equals f of g of x, which is just f of u, replacing u with g of x, that's going to be a differentiable function with respect to x, and is going to be, we're going to find the derivative using these methods. So the derivative of y with respect to x will be equal to the derivative of y first with respect to u times the derivative of u with respect to x. We'll talk more about this method in a future example, but I want to look at this alternative method that is going to be probably the primary way that we're going to talk about the chain rule. So this equivalently can be stated as taking the derivative of a composite function can basically be stated as taking the derivative of the outside function, take the derivative of f, leaving g of x alone on the inside. So you take the derivative of just the outside, leaving the inside alone, times the derivative of the inside. Now, before we can actually get started using the chain rule, we want to first look at function decomposition. That's going to help us with doing the derivative in this method, but also it's going to kind of help us differentiate between what's the inside function and the outside function. So we want to use function decomposition to set up the function for the chain rule. If we're given our composition function here, y equals f of g of x, we need to first figure out what is g of x, and we're going to call that u, and then we're going to rewrite our function in terms of u. So when you're thinking about this, you want to try and simplify your function into something that you know how to take the derivative of and is a simpler derivative to take the derivative of. So in this situation, I've never had to take the derivative of some quantity with an x in it, cubed, take that derivative. I could do this by expanding, but that's a lot of work. So I want an easier method. But I do know how to take the derivative of just something cubed. So if I were to substitute something, if I were to make the inside of this thing that's being cubed something simple, like a u, I know how to take the derivative of u cubed. So we're going to make u this, what's on the inside here. So u is going to be equal to x squared minus 1. So if I was rewriting this function in terms of u, this would just be y equals u cubed. I know how to take the derivative of that. It's going to be 3u squared. Okay? So what would I need to do in this situation? I want to make this a little simpler, so I know how to take the derivative of it. I've never had an x squared inside my sign before, but I know how to take the derivative of just sine of x, or sine of u. So if I make u x squared, this becomes an easier function to take the derivative of. So it'd be y equals the sine of u. So I want you to try and try C and D, see if you can figure out what should u be, and then rewrite your function y in terms of u. So go ahead and pause the video, try and work through these last two parts of this example, and then we'll come back together and talk about this. All right, so for C, we should have said that u was 2x squared minus 3x plus 4, right? Because if I were to get rid of all of this and just replace it with something like a u, I know how to take the derivative of the square root of u. I would rewrite it as u to the 1/2, and then I can take this derivative using the power rule. And so our function would be rewritten as y equals the square root of u, or u to the 1/2 power. Now for part D might have been a little bit more confusing because you might have said, oh, I'm going to make this whole denominator u. And I know how to take the derivative of 2 over u, but I don't know how to take the derivative of x plus 7 to the 4th. I would need to put something in for that as well. So rather than making u the whole denominator, I'm just going to make u what's on the inside of that quantity that's raised to the 4th power. Because if I make u x plus 7, then I get 2 over u to the 4th, like I have here. And using my negative exponents and then power properties, I can take this derivative pretty easily. So this should be what you have for u and then y as a function of u for these two parts. So let's go ahead and take a look at how to find the derivative of this function. So before we use the method where we said dy dx, so the derivative of y with respect to x equals the derivative of y with respect to u times the derivative of u with respect to x. Before we move forward with this piece, which I will show you how to do this in this example, I want to use the other definition, the other derivative. So if I'm trying to take the derivative with respect to x of a composition function, f of g of x, we said it's the derivative of the outside function, leaving the inside alone, times the derivative of the inside function. So u is just the g of x in this situation. So what would be, so let's go ahead and I'm going to move this stuff over. So I'm going to use this method, this one here first. Actually, I'm going to get rid of this here. So let's go ahead and just move this over up here and take this derivative. So in this case, what would be u? What would make this a simpler derivative? Well, I know how to take the derivative of something to the ninth, right? This whole thing to the ninth. So if I just got rid of all of that, the derivative of this is going to be 9 times whatever is there if it was a u, 9 times u to the eighth. And so I can do that derivative. So the outside function is some quantity to the ninth power. So then y prime is going to be 9 times that quantity to the eighth power. So that's the derivative of the outside function, leaving the inside alone, so we don't touch the inside at all when you're doing the first part, times the derivative of the inside. So now we need to take a look at the inside part and take its derivative. So what is the derivative of 3x squared plus x minus 1? Well, 3x squared, its derivative will be 6x. The derivative of x is just 1. The derivative of negative 1 is 0. It's a constant, and we're left with this. So this is the derivative of y. Now, what if we wanted to use that other method, the other method that said the derivative of y with respect to x is equal to the derivative of u with respect to, the derivative of y with respect to u times the derivative of u with respect to x. So the first thing that we would have to do is we'd have to define our function in terms of u. So we said that the inside part would be u. So u would be 3x squared plus x minus 1. And then our function y in terms of u would be y equals u to the ninth. U to the ninth. Now I need a dy du, so I need to take the derivative of y with respect to u. So dy du is going to be 9u to the eighth. So we have that there. And I need to take the derivative of u with respect to x. So the derivative of u with respect to x is 6x plus 1. Now we can see we're multiplying these. Now the reason why this works, right, you can kind of see, is we have these du's that are going to cancel and leaving us with dy dx, which is what we're looking for. So let's go ahead and put all the pieces together. So if we go through this process, we're going to get that dy dx, so the derivative of y with respect to x is equal to the derivative of y with respect to u, so that's 9u to the eighth, times the derivative of u with respect to x, which is 6x plus 1. Now, in the end, I need a function in terms of x. I need a function of y in terms of x. This is not entirely in terms of x. We have this u to the eighth here. So how can I write u in terms of x? Well, I already defined it that way over here. So now I have to substitute that value in for u. So then I get that the derivative of y with respect to x is equal to 9 times 3x squared plus x minus 1 to the eighth, all times 6x plus 1. So this process is quite a bit longer than the original process, as you can see. But I do think this has some good merit to it. It helps you kind of see how to break apart your function and then put together all the different pieces to get your derivative using the chain rule. So I'm probably going to stick with this method for the majority of the problems, examples in this video. But if you prefer this method, feel free to use it when you're doing your homework and going through the the problems on your own. So let's try and take a look at this example. So what is my outside function? What is my inside function? My outside function is, if I were to get rid of what's inside my radical, my outside function would just be the square root of whatever I'm dealing with. My inside function is going to be all of this in here. So remember, when you're taking this derivative, the derivative is going to be equal to f prime of x is equal to the derivative of the outside. And before I actually take this derivative, I'm going to rewrite this as using fractional exponents. So it's going to be 3x squared plus 5x to the 1/2 power. So derivative of the outside function, leaving the inside alone. So I know how to take the derivative of this. I can use the power rule. So it's going to be 1/2 times the quantity that I'm taking the derivative of, and then subtracting 1 from this. So 1/2 minus 1 is negative 1/2. So the inside I left alone is 3x squared plus 5x. And then I need to take the derivative of the inside, so times the derivative of the inside. 3x squared, its derivative is 6x. Derivative of 5x is just 5. And then we're almost there. We want to get rid of the negative exponents. So that negative exponent tells me we're going to get a fraction. This is to the first power, so the 6x plus 5 is going to stay in my numerator. The 2 is already going to be in my denominator because it's part of our fraction. And then it's going to be times this 3x squared plus 5 to the 1/2 power. Remember, 1/2, that just means we're dealing with square roots. So if you wanted to put it back into a square root, you'd have 2 times the square root of 3x squared plus 5. And then we'd have that all over 6x plus 5. So I would take either of these. I would take either of those. Part C. In this example, we want to find the derivative of this function. Again, we're going to use the chain rule. So again, if we're thinking about this and we said, oh, the inside function is going to be that whole thing there. So that's going to leave me with like 6 over x. I know how to take the derivative of that. But that leaves me with this whole thing where we have this quantity to the 5th power. And that's going to be difficult to take this derivative of without using the chain rule. So we're going to need to make the inside just this part here, the 3t squared minus 5. So it's going to give me like a 6 over u to the 5th. But I'm just going to rewrite this again using negative exponents. So this is going to be 6 times 3t squared minus 5 all to the negative 5th power. So here's my inside function. So I'm going to leave this part alone. And I'm going to take the derivative of the outside part. So g prime of t equals, so it's going to be negative 5 times 6, so that's negative 30. Leaving the inside alone, so 3t squared minus 5. We subtract 1 from the exponent, so it's going to be to the negative 6th power, times the derivative of the inside. So the derivative of 3t squared is 6t. Derivative of negative 5 is 0. So we have that. The negative 6 tells me I'm going to have a fraction. The negative 30 and the 6t are going to stay in my numerator. So 6 and 3, that's 18. So negative 180t divided by 3t squared minus 5. All of this to the 6th power in my denominator. All of this to the 6th power. And that would be the derivative of g. In example 3, we are going to have to use the quotient rule, which we didn't have to use in example 2c. But in 3a, we need to use the quotient rule because we have a variable in the numerator and denominator, whereas in part C, we had a constant and then the variables in our denominator. So when we have a constant and then the variables in our denominator, we can just use these power rules and we won't have to use the quotient rule. But in this case, even if I moved this into the numerator, I'd then have to use the product rule. So we're going to have to either use the quotient rule or the product rule, and I'm going to use the quotient rule for this one. And when thinking about this, I'm actually going to, let's kind of refresh our memory on the quotient rule, right? So if I was asked to take the derivative with respect to x of some quotient, u divided by v, we said that that would be the denominator function times the derivative of the numerator minus the numerator function times the derivative of the denominator, all divided by the denominator squared. These aren't to the first. These are u primes and then v primes. Sorry about that. Now, the numerator is, so let's go ahead and name these. I'm going to call the numerator u, and I'm going to call my denominator here v. Let's use a different color. Let's go with this one here. So let's go ahead and look at the derivatives and all of that so we can kind of then just plug everything into this quotient rule. So we know that u is going to be x squared. So then what is my derivative? So the derivative of u is going to be 2x. Here we have v is the square root of x squared minus 3. Sorry, the square root of x squared minus 3, which is the same as x squared minus 3 to the 1/2. Now, when I take the derivative of this, I'm going to have to use the chain rule, right? Because the inside is not just like a simple x. It's not just x. So I don't know how to take the derivative of this to the 1/2 power. It's not just x, it's x squared, and then there's something else tacked onto it. So I'm going to have to use the chain rule on this part. So if I want to find v prime, it's going to be the 1/2, leaving the, so the derivative of the outside function, so my outside function is the something to the 1/2, leaving the inside alone, so x squared minus 3, all to the power minus 1, so 1/2 minus 1 is negative 1/2, and then times the derivative of the inside. So the derivative of the inside is going to be 2x and then a 0, so it's that there. So now we can do a little bit of simplifying here. We have this 2 and 2x are going to cancel. And then we have this negative exponent, which tells me I'm going to get a fraction. So I'm going to have x over x squared minus 3 to the 1/2 power. So this is going to be v prime. This is going to be v prime. So let's go ahead and kind of use all of this information to piece together our quotient when we do the quotient rule here. So let me go ahead and take this derivative. So the derivative of f prime of x, is going to equal my denominator function, which is, I'm going to use the fractional exponents version. So it's going to be x squared minus 3 to the 1/2 power, times the derivative of the numerator, so u prime. Sorry, this isn't du. This should be u prime. U prime. So what is u prime? U prime is 2x minus my original function u in the numerator, so it's x squared, times my derivative of my denominator, or sorry, yeah, the derivative of v. So that's x over x squared minus 3 to the 1/2 power. And then all of this is being divided by v squared. So if I square the square root of something, I just get what's inside the argument there. So it's going to be this x squared minus 3. Now we can clearly see there's a fraction in a fraction here. And we don't want that. We want to get rid of our fraction in a fraction. So we can kind of imagine all of this here being over 1. And to get rid of our fraction in a fraction, we're going to have to multiply by the common denominator of these two pieces. And the only real denominator that isn't 1 is going to be this x squared minus 3 to the 1/2. So we're going to multiply both top and bottom by x squared minus 3 to the 1/2 here. X squared minus 3 to the 1/2 on top and bottom. So when I take this and I distribute it into the first part, we're going to get this x squared minus 3 to the 1/2 times this x squared minus 3 to the 1/2. And when I multiply two things that have the same, the two groups with the power, you add the exponents. So to the 1/2 plus 1/2 is going to be to the first. So that's going to be an x squared minus 3. And then the 2x is going to kind of just tag on for the ride. This x squared and x is going to combine to be an x cubed. So when I multiply this piece into here, the whole purpose of us multiplying by this was so that these would cancel. So I'm just going to be left with my x cubed. So it's going to be minus x cubed, all divided by this quantity here, x squared minus 3. But this time it's to the first times this x squared minus 3 to the 1/2. So 1 plus a half is 3/2. Okay, and then do a little bit of simplifying. So if we distribute here, that's going to give us a 2x cubed minus 6x minus x cubed. So that would be an x cubed minus 6x. So x cubed minus 6x all over this quantity here, x squared minus 3 to the 3/2. Now, some of you might be asking, do I have to factor this in the numerator? And your answer is yes, only if you only have to factor this if it can cancel with something in the denominator. So we can actually just leave it like this. So f prime of x is going to equal x cubed minus 6x all over that quantity, x squared minus 3 to the 3/2 power. So that would be my derivative there. What about this one? So in this, you can see we're going to have to do quotient rule inside of the chain rule. But this whole thing is my inside function. So basically, it's just some quantity that's squared. So if I were to take the derivative of some quantity squared, it's going to be 2 times that something to the 2 minus 1 power. And then it's going to ultimately be times the derivative of the inside. So let's go ahead and try the chain rule on this. So again, this whole thing here is my inside function. So it's the derivative of the outside function. So f prime of x is equal to the derivative of the outside function, which is 2, times some quantity to the first power. And I don't even have to write to the first. And the inside function stays the same. So you leave the inside function alone, 4x minus 1 over x squared minus 2, times the derivative of the inside. And the derivative of the inside is where we have to use the quotient rule. So quotient rule tells me it's the denominator function, x squared minus 2, times the derivative of the numerator. The derivative of the numerator is just 4, minus the numerator function, 4x minus 1, times the derivative of the denominator, which is going to be 2x, all divided by my denominator function, x squared minus 2, that quantity squared. All right, now simplify. All right, so we're going to get 4x squared minus 8, and then distribute a negative 2x in. So negative 2x times 4x is negative 8x squared. And then a negative 2x times a negative 1 is plus 2x, which ultimately simplifies to be, we're going to have this be a 2 times 4x minus 1 in the numerator. If you notice this piece here, the x squared minus 2 and this x squared minus 2, they're going to be multiplying. So this group times this group, that's going to add those exponents here. So let's go ahead and put this together. So x squared minus 2 to the first and x squared minus 2 squared is going to give me an x squared minus 2 to the third. There, like that. Combining like terms, this is going to be a negative 4x squared. So it's going to be times negative 4x squared. 2x doesn't have any like terms, so plus 2x and then minus 8 there. So that would be my derivative of f. So that's f prime of x. All right. What about something like this, sine squared? Well, sine squared really just means the sine of x, that quantity, squared. So if I want to take the derivative of this, it's going to be the outside function, which is some quantity squared, leaving the inside alone, times the derivative of the inside. So f prime is going to be the outside function, so it's going to be 2, leaving the inside alone, sine of x, to the first power, because we subtract 1, times the derivative of the inside, so the derivative of sine is cosine of x. So it's going to end up being 2 sine x cosine x. And if you remember your identities, this is the sine of 2x. This is an identity. So it's one of our double angle identities. And you'll see that come up from time to time in these problems. So just keep an eye out for that. This is kind of the same idea, but we're going to have to do this one is a double chain rule. You're going to have to do a chain rule in the chain rule. So first, let's think about this as the tangent of 4x, this whole thing squared. So we're going to work our way outward in. So the outside function, the whole outside function is some quantity squared. So f prime of x. So the derivative of the outside function, leaving the inside alone. So in this case, the inside is that part there. So it's going to be 2 times the tangent of 4x, all to the first, right? To the first, times the derivative of the inside. Well, what is the derivative of the tangent of 4x? Well, again, we have to use the chain rule again. So if we kind of imagine, right, if we're looking at the outside function, we've already taken care of this one, so now we're just focusing on this. So the derivative of the outside function is the derivative of the tangent, which is secant squared, leaving the inside alone, which is 4x, times the derivative of the inside. The derivative of the inside is 4. So there's that. All right, and now putting all this together, we have a 4 and a 2, so that's going to be 8. So f prime of x is going to be 8 times the tangent of 4x times the secant squared of 4x. And that would be as simplified as you would need to make it. Okay. What about something like this? Now, this is not a product rule problem because notice that the sine does not have an x, right? The cosine is inside our sine function. So it's the sine of the cosine of x. So this is my inside function. So you're taking the derivative of the outside function, leaving the inside alone. So what's the derivative of the sine? Well, the derivative of the sine is the cosine function, leaving the inside alone. So it's times cosine of the cosine, times the derivative of the inside. So the derivative of cosine is the opposite of sine. So we could say then that the derivative of this is going to be, I'm going to pull this out front, the negative, so it's negative cosine of x, whoops, cosine of x times sine of x. So that would be our derivative there. And then the last one for this video is going to be this here. So my inside function, my outside function, sorry, is going to be my e to the x, and then my inside function is what we have here, the 3x. So if this was just like a 4e to the u, what would my derivative be? Well, we know that the derivative of e to the x is just e to the x, so it's the 4e to the u, but so it's the derivative of the outside function, leaving the inside alone. So the inside is this right there, times the derivative of my inside. So the derivative of 3x is 3, which gives me 12e to the 3x.